Okay, natural variables and Maxwell relationships. This is the next topic that we're going to discuss. We've introduced U, H, G, and A now, all right? We also know that we have variables S, T, P, and V for a system. And what natural variables and Maxwell relationships do is they provide relationships between all of these different guys. And so the easiest way to introduce what a natural variable relationship is or what a Maxwell relationship is to just pick one of these functions and show you what we mean by natural variables, show you what we mean by Maxwell relationships. Because if you can see how it's done for one of these functions, it'll be the same for, or the mathematical process will be the same for all of these functions. So again, this is all about mathematical relationships. So we know the combined first and second law gives us du is TDS minus P dV. So this is really interesting in terms of a functional form because we're used to writing these partial derivative identities or these total derivative identities with partial derivatives here. And in fact, we see that we could write this in a partial derivative way. What it looks like from this mathematical perspective is that U is a function of S and V. So from ideas in earlier in the semester, it looks like du, if I write it as a function of S and V, is partial U, partial S at a constant V, ds plus partial U, partial V at a constant S dV. So these are equivalent expressions, okay? So just from the combined first and second law, it looks like S and V are the variables for U. If I write out the actual total derivative, like we've been doing all semester, this is the form I get. Well, if you look at this, there's some equivalence you can see. These terms, if they're equivalent, okay, means that everything in front of the ds in the top and the bottom must be equal to each other, and everything in front of the dv on the top and the bottom must be equal to each other, right? And so it turns out that we can say that du ds at a constant v is equal to t, and du dv at a constant s is equal to minus p. This here, this math, which is pretty simple ideas and combines information between two forms, like in ways we've done before, this is actually how we determine the natural variables of a function, okay? The natural variables are defined by partial derivative identities equaling a very simple variable, right? Partial derivative identities equaling one of our t's, p's, v's, or s's, right? One of our variables that we've been using all semester, all right? So notice that this isn't anything complicated over here. It's not a complicated function like other identities you've seen. It's literally just temperature, okay? So what we say, just from the standpoint of verbiage, is, right, the natural variables of U are S and V. And the way that we know that is because when I write it like this, all right, what I get are partial derivative identities that are equal to plus or minus T, P, V, or S, okay? So then what's a Maxwell relationship? Well, if we use ideas from earlier in the semester again, du, we know, is a state function, right? So we know that the second derivative math or rule applies for U. So if I look at partial U squared, partial V, partial S, it should be equal to partial U squared, partial S, partial V. Remember that second derivative test we did earlier in the semester? It comes into play again here. The Maxwell relationships come from doing this check with the natural variables, okay? So I write U in terms of its natural variables, and now I'm going to do the partial derivative check, knowing that these partial derivatives inside here, right, simplified down to be something pretty simple. So let's take a look here. Remember, there's a different way to write this. I'm just going to give myself a little bit more room here. We could write this as partial v of partial u partial s at a constant v. All of this done at a constant s, right? And we could write this as partial s, partial u, partial v at a constant s, all done at a constant v. Okay? Now I see that I have these identities down here. This is simply t, and this is simply minus p. So I developed the Maxwell relationship now by taking these derivative identities and substituting them into the second derivative test. So this is going to be partial, okay, well that is equal to t, partial v at a constant s, okay, partial u, partial v at s, oh that's minus p, minus partial p, partial s done at a constant v. This is the Maxwell relationship, all right, for u. Now, what you'll notice in Maxwell relationships, the way that you can identify them, okay, is it looks like a derivative equal to a derivative, right? A partial derivative equal to a partial derivative. But what you'll see inside are just, again, P, T, S, and V. Maxwell relationships are all about relationships between those variables of our thermodynamic functions, okay? So one more time, just to recap, for u, what we did is we figured out the natural variable relationships, okay? We then used the second derivative test. The natural variables inside the second derivative test give us the Maxwell relationship, okay? Now, every thermodynamic function will be able to go through a similar process to figure out what the actual values for the natural variables are and for the Maxwell relationship. So let's just do one other example together. So let's pick something like A. So A is something we just introduced. So let's ask ourselves, what are the natural variables of A? Of Helmholtz energy. And then also, what's the Maxwell relationship that we can get from A? Right. And all the Maxwell relationships, again, they have the same components, but they're going to look a little bit different. They're all P, V, T, and S, but they're going to be arranged differently in the partial derivatives. So where do we start? Well, let's write down A's definition. So A looks like U minus TS. Right? A looks like U minus TS. To get at the natural variables, we need to kind of see a total derivative. So we're going to take a dA on this side, a du. We're going to take a d of both sides. We're going to change both sides. Minus TDS minus SDT. Now, these relationships apply for any process, so we're never going to apply keywords here, right? But what we do know is we can always kind of trace things back to the combined first and second law, right? So off to the side, excuse me, off to the side, I know that du is TDS minus PDV. So I can make that substitution in there. So dA looks like TDS minus PDV minus TDS minus SDT. Oh, and amazingly, magically, what happens is terms cancel. And then what you're left with is you're going to be left with a dA that looks like minus PDV minus SDT. Now, what does this tell us? This actually tells us what the natural variables of A are. The natural variables of A, the thing that gives a total derivative of A with simple partial derivatives out in front, the natural variables of A are V and T. Let's write the natural variable relationships then. After our derivation, recognizing that we get this simple form, right, for A, we know that we can write A as a function of V and T, And so dA looks like partial A, partial V at a constant T, dV, plus partial A, partial T at a constant V dt. Here's a dA with a dV and a dt. Here's a dA with a dV and dt. This tells me what the relationships are. If I bring these guys together, right, we should be able to see that partial A, partial V at a constant T is equal to minus P, and partial A, partial T at a constant V is equal to minus S. And again, this is the dV term here. So this and this must be equal to each other, and this must be equal to each other. So the natural variables of A are V and T, and what we have in the middle are the natural variable relationships. And again, very important ideas. This gives, partial derivative identity that we've derived that's incredibly powerful, because the thing over here is just real simple. So we can imagine taking this, and I'll do an example in a bit here, but we can imagine taking this now and analyzing dA for an isothermal process, okay? Bringing the dV to the side and integrating. And all we really need is P information about what our gas is doing to analyze what that value is, okay? So here are our natural variable identities. Let's take it a step further. And then with these identities, let's go ahead and apply the second derivative test. I'm going to jump to the most useful form of the second derivative test right away. So A is a state function, right? So it applies, so anything we can say about a state function applies to A. So if I take partial T of partial A, partial V at a constant T, and I do that at a constant V, that should be equal to partial V, partial A, partial T at a constant V, all done at a constant T. So that is essentially the second derivative test. But what do we see here? We see that from our natural variable relationships, this partial derivative is simply minus P. And we see from our natural variable relationships that this partial derivative relationship is actually minus S. So we make those substitutions in there, and let me use a different color. What we're going to get is partial minus P, partial T at a constant V, plug this in there, is equal to partial minus S, partial V, all done at a constant T. The negative and the negative on each side cancel, and what we're left with is partial P, partial T to constant V, is partial S, partial V at a constant T. Again, we see inside our Maxwell relationships that what we have is a situation where we just see P's, T's, and V's, and S's all relating each other. So again, for A, these are the natural variable relationships. This is the Maxwell relationship right down here in red, okay? And the last thing I'll say is that if we look at this Maxwell relationship, this is actually one of the more important Maxwell relationships that we can derive. They're all important in their own ways. But again, whenever you see things related with just P, T, and V, oh man, that's really great, because then all that gas law stuff that we did throughout the semester applies. So what I'm going to do is I'm going to rearrange this, and I'm going to solve for ds. So ds, right, looks like partial P, partial T at a constant V using this Maxwell relationship. I have to take the dV to the opposite side. I'm going to remind myself that this is for an isothermal process, right? Isothermal. So then what I can do is I can integrate both sides, and I get a delta S. And delta S now is going to be equal to V1, V2, integral, partial P, partial T at a constant V dV. And so then all you really need to know about your gas is how pressure changes as temperature changes at a constant volume, and it's an alternate way to get delta S. Okay. This is for an isothermal process, but again, any partial derivative identity that we derive, and the Maxwell relationships are partial derivative identities, they can always be integrated in a first order fashion to get at deltas, to get at changes for certain types of processes. Okay. So what I'd like you to do is, even though it's in your book, try based off of this explanation that we've just had to go through and figure out what the natural variables of G are yourself, all right? And make sure you can carry out the derivation, start with the definition of G that I've given you, and then plug in as needed, all right? In terms of identities that always go back to the combined first and second law, but you should be able to show with a derivation that G is a function of P and T. And then from there, you should be able to get to the Maxwell relationships. Similarly, what I want you to do for H is go ahead and show that the natural variables of H are actually S and P. And for each, build the natural variable relationships and get the Maxwell relationships. What you'll notice in your book is there's table 22.1 on page 899. That encapsulates everything that we've done today in terms of getting to a Maxwell relationship. But honestly, based off the lecture that I just gave you, try to do these on your own and then confirm the information inside this table about what those Maxwell relationships are. As you derive a Maxwell relationship, as you derive a natural variable relationship, also imagine integrating them to get at useful information.